All right, so before we start talking about the exponent laws, let's just review where we might see exponents. Okay, so, and I want to talk about some of the vocabulary as well. All right, so if we have something like 5 cubed, okay, what's the value of 5 cubed? 5 to the power 3, or 5 raised to the exponent 3. 5 times 5 times 5, that's right. And what's that value? Yep, 125, right, okay. Okay, so some vocabulary. This whole thing is not called an exponent. A lot of people think it is. The whole thing is called a power. Okay, power has two parts. It's got a base, which is 5, and it has an exponent. Now, powers are used as a shorthand way to write out repeated multiplication. Okay? And in fact, if you go all the way back to, like, I don't know, grade 1 or 2 or 3, it's very similar to the relationship between addition and multiplication. Multiplication is just a shorthand way of writing repeated addition. So if you have 3 times 7, 3 groups of 7, 7 plus 7 plus 7, it's the same sort of idea. Okay? It's a shorthand way of writing repeated multiplication. This is the value of the power. This is the expanded form. We don't typically, once we get up to this level, deal with that a lot, but sometimes we do. Okay? So that's some vocabulary. Okay? Now we have some laws, these are exponent laws, that we can use to simplify expressions that contain exponents. Okay? And these are sort of in no particular order, but I do want to talk about them. So first one is the product law. And this one basically states that when you have two powers that have the same base and you multiply them together, you can add their exponents. So this can be written, because the base is both x, as x to the m plus n. Okay? Now, why does this work? So I kind of want to write the y here. It all comes down to expansion. Okay? So if I have, for example, a cubed times a squared, a cubed is a string of 3 a's multiplied together. So a times a times a times a squared is 2 a's multiplied together. And then all together, if you look at how many a's there are multiplied together, there's 5 of them. Okay, that's called the product law. Okay. All right, the quotient law. So when we multiply two powers with the same base, we add their exponents. What do you think we're going to do when we divide two powers with the same base? Subtract, exactly. So x to the m over x to the n is going to be x to the m minus n. Okay? And again, if we want to know why, we can look at expansion. So let's say I have a to the 6 over a cubed. Okay? Now, if you don't think, if you do this too fast, I get a lot of people say that's a squared, because when you see the fraction line, you're used to reducing, right? But if you think about what this is expanded, it's a times a times a times a times a times a, 6 of them in the numerator, and 3 of them in the denominator. Okay? Now, anytime you have the same factor in the numerator and denominator, anything divided by itself is equal to 1. So these cancel because a over a equals 1. And then a over a again equals 1. And finally, a over a equals 1. And so we're left with 3 of them. Okay, so this is why these things work. Okay, then there's the power of a power law. So if I take a power, x to the m, and I raise it to another exponent, I can simplify that by multiplying the two exponents together. So this is going to become x to the m times n. Okay, now why is that the case? Let's try it. If I have a squared cubed, let's say, okay, this cube means I multiply whatever comes before it by itself 3 times, right? What comes before it is the bracket a squared. So this is going to be a squared times a squared times a squared, right? And if I expand each of those out, a times a times a times a times a times a. And then if you look at how many we have 6 of them. Okay? All good so far? Yeah? Okay. So power of a product. So if my base itself is a product, meaning I'm multiplying two things together, like x times y. Or often you'll see the product of a number and a variable. 2a, for example, or 7b, or whatever it is. And you take that product, and really it's the same thing for a quotient as well. If you're dividing two values and that's your base, and you raise those to another exponent, we can apply that exponent to each part of the product. Okay? So right now, in fact, there is an exponent on x, it's 1, and there is an exponent on y, it's also 1. And so what we do is we multiply both of these by m. So, x to the m, y to the m. Okay? Sometimes that exponent on the product is a 1, sometimes it's not, right? So for example, if I have something like ab squared squared. Okay, thank you. Again, this 2 means I multiply that by itself twice. So ab squared times ab squared. And if I expand these out, a times b times b times a times b times b. And if I count now, group the same variables together, I've got 2 a's being multiplied together and 4 b's being multiplied together, right? So this is essentially a squared b to the 4, right? And the reason why I can do that is because with multiplication, order doesn't matter. 3 times 5 is the same as 5 times 3. So I can say, okay, those 2 a's make a squared, and these 4 b's make b to the 4. Okay? Of course, this is just showing you why. In reality, what you're going to do is say, oh, there's an exponent of 1 here and 2 there, so I'm just going to go 2 times 1 is 2. It's going to be a squared. 2 times 2 is 4. It's going to be b to the 4. Right? This is just the y. This is very similar. I'm not going to do an expansion here because I'm hoping you guys will see how that works as well. But this is essentially, again, if it's a quotient, you just distribute to each part. So x to the m over y to the m. Okay, we could do, let's do one. Let's say I have a over b cubed. Okay, expand it out, a over b times a over b times a over b. When you're multiplying fractions, you multiply all the numerators together, multiply all the denominators together. So this becomes a cubed over b cubed. Okay? Negative exponents. As long as the base isn't 0. X to the negative m. How would you evaluate like 3 to the negative 2? You guys remember that? Maybe all the way back from your 10C days.
You put the negative in front of the x.
Oh, okay. You're actually thinking more along the lines of logarithms. So we're going to do something that looks kind of like that with logarithms, but no. This actually, we define it as 1 over x to the positive m. Right? So if you have like 3 to the negative 2, 1 over 3 squared, which is 1 over 9. Okay? Now this actually, the y, it's not a very satisfying answer. It's by definition. Mathematicians have decided this is how we are going to define negative exponents. However, it does actually work out really nicely with some of the patterning that we see. So for example, I'll just show you, this is sort of the y. I'll do a little star here and then do a little star here, right? So why did they choose to define negative exponents that way? Well, probably because if I look at some patterning, let's say I look at 2 cubed, 2 squared, 2 to the 1, 2 to the 0, 2 to the negative 1, 2 to the negative 2. Okay? What I'm doing here, I start with something that's defined, like 2 cubed. And I know what that's equal to. And then I slowly decrease, or 1 by 1, I suppose, I decrease my exponent by 1. And I'm going to try and see if I can establish a pattern. Okay? What is 2 cubed? 2 times 2 times 2. Yep. 8. Good. 2 squared? 4. 2 to the 1? 2. Okay. So let's just start by looking at some patterning that's going on. When I decrease the exponent by 1, what happens to my value? Halving. Yes. So I'm dividing by 2. Divide by 2, right? Now, what do you think 2 to the 0 is going to be? 1. 2 divided by 2 is 1. This is also by definition. Okay? 2 to the negative 1. If I cut this in half, yeah, it's a half. Right? And then if I cut a half in half, half of a half, quarter, yes. Okay? Well, 1 over 4 is the same as 1 over 2 squared. So we go from here to there. Right? So why does the definition kind of make sense? It fits in with this patterning that's happening. Okay? All right. And then finally, rational exponents. Do you guys remember what, like, I don't know, 25 to the power 1/2 is? Put that in your calculator. 25 to the power 1/2. Exactly. Yeah. What is 25 to the 1/2? 5. Yeah, so just like you were saying, that's the same as taking the square root of 25, right? So rational exponents, when the exponent itself is a fraction, that can be written as a radical. And in general, if you are converting this into a radical, the denominator of the exponent always becomes the index of the radical. And then the numerator of the exponent that goes on the outside. Okay? So for example, let's say I wanted to know the value of 25 to the 3 over 2. Okay? So when I'm converting, I'm going to think, okay, I'm going to put my radical symbol in. The base of the exponent, of the power rather, becomes the radicand, the number on the inside. The 25 is going to go here. What's the index? This guy. What should go here? 2. It's a square root of 25, and then I'm going to cube it. Okay, so what is the square root of 25? 5 cubed. So that's 125. Yeah? Okay, cool. All right, so we're going to practice this a little bit. I think I'm going to actually get you guys to practice it. So yeah, I'm going to give you guys some time to practice it. What I'll do is after a couple of minutes, I am going to write the answers down. And then we can discuss some of them if necessary. Does that sound good? All right. You only move the exponents that are negative. If you have a product and in one part of the product you have a positive exponent, in the other part you have a negative exponent, leave the part that's positive where it is. So what this actually is it's 3 to the 1 times x to the negative 3. Okay? This is the one that's negative. So this is going to become 3 to the 1 times 1 over x cubed. Right? Now, we could superficially put a denominator of 1 in here. And then when you multiply exponents together, you multiply the numerators and you multiply the denominators. So that's going to give us the 3 over x cubed. Okay? With number 7, one thing that could be helpful to do in your mind, and if you need to write it down, that's fine as well, is to reorder the multiplication, right? So everything here is being multiplied. 4 times y squared times 2 times y to the negative 3. So think about it this way. 4 times 2 times y squared times y to the negative 3. Okay, now 4 times 2 is just 8. Y squared times y to the negative 3. Here I'm going to use my product law, where I add exponents. And 2 plus negative 3 is negative 1. Okay? Now this actually looks, at this point, very similar to number 6. So this is the only exponent that's negative. The 8 is 8 to the 1. That's positive. So this is going to become 8 times 1 over y to the 1. You don't have to put that 1 in there if the exponent is 1. And remember, this is 8 over 1. And that's 8 over y. Okay? And by the way, I expect that when you simplify these, it takes you several steps. And you write them all down, right? So I can only do this in my head because I've been doing this since like grade 9 math, which is a very long time ago. And I do it all the time, every day, all day long. So I can do it in my head, right? But that's not the expectation. The expectation is that you at least get to this spot maybe, and then go to the next line, right? Okay, so let's talk about this one. Now, in this case, you have to think about order of operations. Okay? We're multiplying 3 by this bracket, right? But then this has an exponent on it. What do I have to deal with first? Okay, but within the brackets, is there anything that I could do? No, yeah, so between the multiplication and the exponent, I got to deal with that first. So this 2 has an exponent of 1 on it. So I'm going to distribute this in here. And I leave that 3 times whatever alone. So 3 times, this is now going to become 2 to the 4, x to the 12. Okay, now 2 to the 4 is 16. So 3 times 16 is 48. Okay? And finally, in the last one, this is set up like division. So I would think in terms of quotient law. The 3 is just 3. That's 3 to the 1. I'm not going to do anything with that. But here I've got a to the negative 4 divided by a to the negative 3. So with the quotient law, when the bases are the same, we subtract exponents. So this is going to become 3a to the negative 4 minus negative 3. Be careful there because we're subtracting a negative value, right? That actually becomes addition. And that's 3a to the negative 1. And very similar to what this one looks like, right? So that's where the 3 over a comes from. Right? And one thing that some people like to do also, think about this as having a denominator of 1. If it's negative in the numerator, bring it down to the denominator. If it's negative in the denominator, bring it up. Does that make sense? So far, so good? Okay, cool. All right, next. Determine the exact value without the use of the calculator, then verify with a calculator. Okay? So 2 to the negative 4, we've already talked about how do we define these. We want to know the value. It is 1 over 2 to the 4. And what's 2 to the 4? 16. So 1 over 16. Okay? 27 to the 1/3. Where would you start with that one? How do we interpret rational exponents?
Could you just put it into the, what it's called?
This thing, the radical, yes.
Yeah.
This becomes a radical, right? So draw your radical symbol. The 27 goes in here. The denominator is the index. And then if the numerator is 1, you don't need to put anything in, right? So we're looking at the cube root of 27, and that is 3. Okay? 2 to the 0. 1. And 64 to the negative 1/2. Okay, so, yep. 1/8, very good, yes. So there's a couple things that we need to deal with this question. One of them is the fact that the exponent is negative, and the other is that it's fractional. And you can actually do it in either order. I personally, and this is just, I don't know, creature of habit, deal with the negative part first, right? But you don't have to. I can show you how to do it both ways. If you deal with the negative part first, this is going to become 1 over 64 to the 1/2, right? And 64 to the 1/2 is the square root of 64. The square root of 64 is 8. Okay? Or you can deal with the fractional part first. The only thing that you need to remember is that an index cannot be negative. So when you have something like this, and this is a little bit of a tangent, but sometimes it creates confusion, so I'm going to talk about it now. A negative fraction, negative 1/2, can be written like this or like this. These are all equivalent to each other, and they mean the same thing. So when you have a negative fractional exponent, what you need to think about is that the index is the denominator. That can't be negative. So you kind of have to go with this middle version, right? So if I'm taking 64 to the negative 1/2, then the index of 2 must be positive, and the negative 1 goes on the outside. Okay? Square root of 64 is 8 to the negative 1, which is 1 over 8. Okay, so it works both ways. One question that I have before we move on, exact value. What does that mean? No, so there's exact versus approximate. Those are the two, that's the difference. And in fact, all of these, if we converted them into decimal approximations, would in fact be exact. Give you another example, actually, that hopefully will make it more clear. Okay, so I'm going to take out a calculator, and I'm going to look at, I don't know, square root of 7. Okay. So the square root of 7, 2.646, let's say. One of these is exact, one of them is approximate. Which is which? Yes?
The square root of 7 is exact.
Yeah. Square root of 7 is exact. The decimal approximate, it's actually called a decimal approximation, is approximate, because we round. It's not exactly equal to this. There are more decimal places that are going on. Okay, so this is exact. This is approximate. Okay? All rational numbers, meaning you can write it as a fraction, can be written exact in decimal form. Sometimes they're repeating, like 0.22222, but you can write it with a little bar on top, and then it's an exact value. Okay, so I just wanted to talk about that because this will come up several times throughout this course, this idea of exact versus approximate. And on a multiple choice, let's say diploma exam, if they asked you for the exact value of something and the answer was the square root of 7 and it was multiple choice, they would give you both answers because they want to put that in as a distractor because they're trying to also assess, do you know what exact means, right? So I just want to make that point. Okay, so this up to this point is review. We're now going to start to work towards building some skills that we will need to solve exponential equations, which is a big part of this outcome. Okay? One of those is a change of base. Okay? A change of base is essentially when we have a power with one base and we want to change that base into another power with another base. And it only ever works if the original base can be written as a power with a different base. Okay? So for example, let's say I wanted to change 16 to the 3x to base 4. Can we write 16 as a power with a base of 4? Yep.
The square of 4.
Yeah, exactly. So 16, I'm going to switch back to black actually. 16 is equal to 4 squared. So if I want to change this expression to another expression that has a base of 4, what I'm going to do is a substitution. I'm going to replace 16 with 4 squared. Okay? Now, here I have a power. I'm raising it to another power. What do I do with those exponents? Multiply, exactly. So this is going to become 4 to the 6x. This is called a change of base. And this is very frequently a step that's involved in solving an exponential equation. Okay, let's try this one. 27 to the x plus 1 to base 3. So if we want to change this to base 3, first thing you need to ask is, can you write 27 as a power using a base of 3? And what would it be? 27 cubed. Yep. So 27 is 3 cubed. 27 to the x plus 1 is going to be something to the x plus 1. And that something is 3 cubed. Okay. Now, we also want to multiply the exponents. What I find is helpful to do is actually, if it's a binomial exponent, to put brackets around it, because that 3 needs to be multiplied by both parts. Right? So this is going to become 3 to the 3x plus 3. Okay? So I would like you guys to try these two. Oh, there's 4 of them, actually. Try these two. In fact, I'm going to rewrite these on the next page, so I can just all write the answers all on one page. So 125 to the x plus 2, 32 to the x minus 2. OK. I'll write that up here. Okay, and I'm going to get you guys to work on that for a couple minutes. to base 2. Okay, now when you see this sort of thing, focus first on changing the denominator base to base 2. So ignore the fact that it's in a fraction initially. Okay? If we just focus in on the 64, how can we write 64 as a power with a base of 2? 64 is 2 to the what? Yeah, 2 to the 6. Okay, so 64 is 2 to the 6. So what I'm going to do is I'm just going to replace the 64 down there with 2 to the 6. So this becomes 1 over something to the x, and that something is going to be 2 to the 6. Okay, now of course we can multiply these together. So this is going to become 1 over 2 to the 6x. Okay, we're almost there, but this actually does not have a base of 2 yet. It actually has a base of 1 over 2. Okay, so this is not something that we typically do when we taught you exponent laws back in grade 10. But if we want this to be a base 2, we need to bring it up to the numerator. If it's in the numerator, if it's positive in the denominator and we bring it up, what's going to happen to that exponent? It'll become negative, exactly. Oh, whoops, 1 over, 2 to the negative 6x. Yes, and now it has a base of 2. Okay. All right, is that good so far? Yeah? All right. So we're going to start talking about exponential equations today. We'll finish this tomorrow. But I want to talk about what is an exponential equation and what are some ways that we can solve it. And we're going to start, there's a couple of methods that we can use. We're going to start, though, with a change of base, with using that strategy of changing the base to see if we can make something work. Okay? So let's just talk about what is an exponential equation. An exponential equation is an equation, surprise, surprise, in which the variable or the unknown is in the exponent position. Okay, so a very simple exponential equation could be something like this. 3 to the x equals 9. What is x? 2, right, because 3 squared equals 9. Okay, so this is one that you could do in your head. Really what you're doing, though, in your head is you're thinking in terms of change of base. You're thinking about, how do I write 9 as a power with a base of 3? And then what would the exponent be? Okay, so really what's going on here is I'm going 3 to the x equals 3 squared. 9 is equal to 3 squared. Yes? Yes. Okay, and when you are solving an exponential equation, if the bases of both sides are the same, we can conclude that their exponents must be the same as well. So once you get to this stage where the bases are both 3, you can drop the bases and set the exponents equal to one another. So we can now conclude that x has to equal 2. Okay, so the idea is that we change one or sometimes both bases on both sides to be the same base. And once the bases are the same, we can drop them and set the exponents equal to one another. Okay? When the exponents are equal to one another, we'll have a linear equation. And you guys have been solving those for a very long time. So of course, we will practice it a little bit, but solving a linear equation, which is what we'll have when we drop the bases, should be, something you've seen before. Okay. No? Okay. Sorry, I don't know what I did when I printed, but it looks like I must have deleted some space at some point, and everything starts a little bit above where it did before. That was my bad. Okay, are we okay? We're good? All right, so we're going to practice this. When you are solving an exponential equation, one of the first things first thing you should do is you want the power to sort of be isolated. You don't want to multiply it by a number. So if you have to do that, then divide that first. And we'll see an example of that. But if you have the power isolated, you want to look at both sides and say, OK, I have 7 to the x minus 2 and 49 to the 2x minus 3. One of my bases is 7. The other one is 49. Is there a base that I could choose that would work for both sides? Yeah, 7 will work, right? One of them already has base 7. 49 is 7 squared. OK? So first thing you want to do is, I'll write number 1. Find a base that works for both sides, if possible. Okay, so in this case, we can use 7, right? We don't need to do anything with the left side. That's already using base 7. But I'm going to replace the 4. Whoops. Okay, and then if you need to, do some simplification with those exponents. So I'm not going to do anything on the left side, but on the right, I can do this distribution. Right? So this will be 7 to the x minus 2 equals 7. 2 times 2x is to the 4x, and then minus 6. Okay, and in fact, at this point, I'm actually going to take the brackets away. We don't really need brackets here anymore. Okay? So once we're at this stage, the second thing that we can do is drop the bases. So what we'll have is, if we drop the bases, is we're going to have x minus 2 equals 4x minus 6. And at this stage, we should have a linear equation. So we are going to now solve the linear equation to determine the value of x. Okay? And we solve these using opposite operations, right? Now, when you are solving a linear equation, the sort of penultimate goal, the ultimate goal is to isolate x, right? The penultimate goal, the step before you isolate x, is you want to collect your variables on one side of the equation and collect your numbers on the other side. Okay? So what I tell, because sometimes this seems like an easy step, but sometimes people really struggle with it. For some of you guys, this is easy peasy breezy, right? You can just do it probably in 15 seconds. But if you are still struggling with linear equations, then what I recommend that you do is pick a side for your variables, pick a side for your numbers. Move what doesn't belong using opposite operations. Okay? So let's say, I don't know, this is my variable side, and this is my number side. Okay? Well, on my variable side, The x is fine, but I have to get rid of this negative 2. How do I do that? Add 2 to both sides. Okay, that's good. Now if I look at my number side, I've got the negative 6 plus 2. That's fine. I got to deal with this negative 4. Or sorry, the 4x rather. How do I undo that? Subtract. Take it away. If you have it there, take it away. Okay. Now by design, 2 of these operations make 0. That was the whole point, right? So negative 2 plus 2 is just 0. That's gone, so I don't need to worry about that. And then 4x minus 4x is 0 as well. And so I would probably write this on the line below, but I'm running out of space. I can write it down here, I guess. X minus 4x, how much is that? Not quite. It's like you have 1x, and then you take 4 of them away. Negative 3x. Yes. And then on this side, negative 6 plus 2 is negative 4. OK, so this was that like penultimate step, the step before the last step. How do I isolate x now? Divide by negative 3, right. OK, and then of course, negative divided by a negative is positive, so x equals 4 over 3. OK, now verification. I think I asked you to verify. Did I ask you to verify? All right, we'll do the verification up here because I am running out of space. OK, verification means you take the original equation and you plug x equals 4 over 3 into the left side, and you plug it into the right side, and you make sure that they are equal to one another. You can do this using a calculator. OK, so when you verify, you know what? I'm not going to do it above. I'm going to do it down here. I'll extend this a little bit. OK, when we verify, right, you want to think the left side on the right side. This is how I like to set it up. The original equation was 7 to the x minus 2 equals 49 to the 2x minus 3. Okay, so what we're going to do is on our calculators, we're going to go 7 to the 4 over 3 minus 2. Okay, so here we go. Seven to the power, in brackets, 4 divided by 3 minus 2, bracket, equals, okay, 0.2733, let's say. 0.2733. Okay, on the right side, we're going to go 49 to the power 2 times 4 over 3 minus 3. And on your calculator, you're going to go 49 to the power. One thing that's sort of important is that you do put, whatever numbers go in there in brackets. So it was 2 times 4 divided by 3 minus 3 equals. Same thing. Okay, that's good. That's all we need. Okay, so we have that the left side equals the right side, and that is what we want, right? We're good. Okay. All right. Next question. So this is what I was getting at the beginning, where before you start changing bases, make sure that your power is isolated. Yes? Yeah. Okay. So my power, the 3 to the 2x, is not isolated right now. It's being multiplied by 4. So what should I do first here? Yep, divide both sides by 4. Okay? And then what I'm going to have is 108 over 4 happens to be 27. Okay, now at this stage, hopefully we can see what we have to do here. What would your next step be? Yep. Right, change 27 to 3 cubed, change a base. Right, so we're going to get 3 cubed equals 3 to the 2x. Okay, and now what can we do? Drop the bases. 3 equals 2x. And we are going to then divide by 2. Okay, so x equals 3 over 2, or 1.5. And that's it. What really stumps people with this type of question, though, is that if you don't recognize that you have to divide by 4 first, you're kind of hooped. So that's a really important step, that the power must be isolated. Okay, we're going to do one more question, and then we'll call it. That'll be it for today. And then what I'd like you to do are these practice questions for homework. Okay? So next question, explain how you could estimate, without the use of a calculator, the solution for x to the nearest tenth in the equation 6 equals 3 to the x. Okay, so how do we estimate without the use of a calculator? Okay, well, firstly, are we able to do a change of base here? One of our bases is 3. We really actually can't go smaller than that because 3 itself is prime. So I can't make that one smaller. Can I write 6 as a power with a base of 3? No, 3 to the 1 is 3. 3 to the 3 squared is 9. 6 isn't in that list, right? So what I want to do, I can't change the base here. But what I can do is I can estimate what the exponent would be based on those benchmarks of the fact that 3 to the 1 is 3. 3 squared is 9. 6 is right in the middle. So approximately, what do you think the exponent would be? Yeah, 1 at 1.5. This is approximately 3 to the 1.5. So if I'm approximating, I can say, I start with this, 6 equals 3 to the x. I can say, OK, 3 to the 1.5 is approximately 3 to the x. And I conclude that 1.5 is approximately x. Okay? Now, this is a perfect explanation. You do not need to write an essay, right? Explain means make clear what is not clear. If I see that number line, I can see exactly where you get that approximation from. And that's totally fine. Okay? So what I'd like you to do for homework, and I think this might be a little different from D2L because I wasn't exactly sure where we'd get to today. I want you to do the practice questions 1 on page 45 and 2 on page 46. Okay, so that is your homework for tonight. You can start on it now.